In this video, we started chapter 7 of our textbook, where we study network flow problems. Network flow problems are a special type of linear programming problems. Some special cases are the assignment problem, the transportation problem, the maximum flow problem, and the shortest path problem. We have already seen at the beginning of the course the assignment problem. And in this chapter, we will also discuss these other three types of network flow problems that I just mentioned. In any case, network flow problems arise naturally in several real-world optimization problems, especially in the analysis and design of communication, transportation, and logistic networks. Since the network flow problem is a special case of linear programming, any algorithm for linear programming can be directly applied. However, in this chapter we're going to study them separately because these problems share a very special structure, which allows us to solve these problems much more quickly. In fact, the structure of these problems can be used to simplify the simplex method, and it can also be used to develop new completely different algorithms to solve these problems. In this chapter, we will study a primal method for network flow problems. Like the primal simplex, this is a method that maintains feasibility and at every step it improves the objective value. In this chapter, we're going to see section 1, 2, and 3. We start with a brief introduction to graphs, which is fundamental since network flow problems are defined on graphs. Then in section 7.2, we formulate the network flow problem. And finally, in section 7.3, we develop the network simplex algorithm. So let's now start with section 7.1, where we discuss graphs. We're going to see both undirected graphs and directed graphs. Let's now start with undirected graphs. At the top of this slide, we have an example of an undirected graph. In particular, we have 5 nodes, which I call 1, 2, 3, 4, and 5, and some of them are connected by a link that we're going to call an edge. Formally, an undirected graph is an ordered pair NE, where N is a ground set, which is called the set of nodes, and E is a set of edges. An edge is defined as an unordered pair of distinct nodes. So essentially, it is just a subset of cardinality 2 of N. Therefore, we're going to denote an edge using the standard notation for sets. When we work with graphs, it is standard to denote the number of nodes by n and the number of edges by m. Now that we have formally defined a graph, we can formally write down the graph in our example. The set of nodes is the set containing 1, 2, 3, 4, and 5, and the set of edges is the set that contains the set 1, 2, which is visualized by this link between 1 and 2. Then we have the sets 1, 3, 2, 3, 1, 4, 3, 4, and 3, 5. Since an edge is simply a set, we can write the same edge as the set containing ij or the set containing j and I. Note that we required edges to contain exactly 2 nodes. Therefore, the set containing the same node twice cannot be an edge. It will be useful to define the concept of incidency and of n nodes. We say that the edge ij is incident to the nodes I and j. Furthermore, the nodes I and j are called the end nodes of the edge ij. For example, the edge 2, 3 has end nodes 2 and 3, and it is also incident to node 2 and to node 3. The degree of a node is defined as the number of edges incident to that node. For example, the degree of node 3 is equal to 4 because the node 3 is incident to the edges 3, 2, 3, 1, 3, 4, and 3, 5. The degree of an undirected graph is defined as the maximum of the degrees of its nodes. In particular, you can check that the degree of the graph in our example is equal to 4. A walk from a node I1 to a node IT is defined as a finite sequence of nodes I1, I2 until IT. In this sequence, every pair of consecutive nodes must be an edge. So I1, I2 must be an edge, I2, I3 must be an edge, and so on and so forth. In our example, let's consider nodes 2 and node 5. Of course, there are several walks from node 2 to node 5. One of them, for example, is 2, 1, 3, 4, 3, 5. A path is defined as a walk that has no repeated nodes. So the walk that we just saw in the example is not a path because we repeated several times the node 3. An example of a path from 2 to 5 is given by 2, 3, 5. We say that an undirected graph is connected if there exists a path joining any pair of distinct nodes. You can check that in our example the graph is connected. A cycle is defined as a walk from I1 to IT such that all the first t-1 nodes are distinct, while the last node must be equal to the first node. Furthermore, the number of distinct nodes in the walk must be at least 3. In our example, a cycle is given by 2, 3, 1, 2. The reason we require to have at least 3 distinct nodes is because we want to exclude a walk of the type 2, 1, 2. And this is because we don't want to traverse the same edge twice back and forth. Next, let's discuss directed graphs. Like in the undirected case, we start with an example. Here we have again 5 nodes, 1, 2, 3, 4, and 5. But now instead of edges we have arcs. Essentially the difference between edges and arcs is that arcs have a direction, which is visualized in the picture by an arrow. Formally, a directed graph is an ordered pair NA, where N is a set of nodes and A is a set of arcs. An arc is defined as an ordered pair IJ of distinct nodes. Note that to distinguish arcs from edges, we use a different notation. In fact, here we use parentheses, while for undirected graphs we use the braces. Note that it's fairly standard in mathematics to use parentheses for ordered pairs. For example, we use parentheses also here because NA is an ordered pair. In fact, in a directed graph, of course, you cannot switch a node with arcs. So as opposed to the undirected case, in a directed graph, both ij and ji can be arcs. In our example, we have the arc 2, 1 and the arc 1, 2. This now makes sense because these two objects are different. Like in the undirected case, also here, arcs that contain twice the same node are not allowed. Also here, we're going to use the same notation regarding the number of nodes and number of arcs in a directed graph. We're going to use n to denote the number of nodes, and we're going to denote by m the number of arcs. Now that we have defined a directed graph, we can now write down formally the directed graph in our example. The node set is the set containing 1, 2, 3, 4, and 5, and the set of arcs is the set containing the arc 1, 2, which is this arc from 1 to 2, the arc 2, 1, which is the arc from 2 to 1, and then the arcs 1, 3, 3, 2, 1, 4, 4, 3, and 3, 5. For any arc ij, we have a way of referring to I and j separately. Namely, we call I the tail and j the head of the arc. Also, we say that the arc ij leaves from node I and it enters node j. It is also incident to both nodes I and j. For example, if we look at arc 3, 5, then 3 is the tail and 5 is the head. The arc 3, 5 leaves from node 3 and enters node 5. The same arc 3, 5 is also incident to both nodes 3 and 5. Next, we introduce a notation which is somewhat similar to the notation of degree in undirected graphs. However, there are several differences. Here we have tails and heads, so we're going to differentiate between the two by defining two different objects. First, we define a delta in of a node I, and this is the set of tails of arcs that are entering node I. So formally, delta in of I is the set of all nodes j such that ji is an arc. Symmetrically, delta out of a node I is the set of heads of arcs that are leaving from node I. Formally, delta out of I is the set of nodes j for which ij is an arc. For example, let's consider the node I equal to 3. Then delta in of I is the set containing 1 and 4. On the other hand, delta out of node 3 is the set containing the node 2 and the node 5. Sometimes it will be useful to us to construct an undirected graph starting from a directed graph. The way we do this is we simply pick our directed graph and we just ignore the direction of the arcs. For example, the arc 1, 4 just becomes the edge 1, 4. If it happens that between two nodes we have two arcs, like in this case where we have arc 2, 1 and 1, 2, then in our graph we will simply have one edge between 1 and 2. This allows us to define easily some concept for directed graphs that we've already defined for undirected graphs. For example, we say that a directed graph is connected if the resulting undirected graph is connected. In particular, our example of directed graph is connected. Next, we define the concept of walk for directed graphs. A walk is defined as a sequence of nodes I1, I2 until IT, together with an associated sequence of arcs A1, A2 until AT-1. Now these two sequences must be linked in a very specific way. Namely, every arc AK in the sequence must either be the arc IK plus 1 or the arc IK plus 1 IK. In the first case, we say that AK is a forward arc, and in the second case, we say that AK is a backward arc. In our example, a walk is given by the node sequence 1, 2, 3, with associated arc sequence 1, 2, and 3, 2. In particular, the arc 1, 2 is a forward arc, while the arc 3, 2 is a backward arc. Essentially, this means that we're going from 1 to 2, traversing the arc 1, 2 forward, and then we're going from 2 to 3, traversing the arc 3, 2 backwards. This example should also clarify why the definition of walk for directed graphs is more complicated than the one for undirected graphs. The main difference is that here we have the associated sequence of arcs, which we didn't have for undirected graphs. This sequence of arcs is clearly needed, because in our example, if we only give the sequence of nodes 1, 2, 3, it's unclear how we go from 1 to 2. We could either go by traversing forward the arc 1, 2, or we could go by traversing backward the arc 2, 1. In a directed graph, a path is defined as a walk with all distinct nodes. The example of walk that we just gave is also a path. Instead, a cycle is a walk where all the nodes but the last are distinct, and the very last one is equal to the first. Note that, as opposed to the definition of cycle for undirected graphs, here we don't require to have at least 3 different nodes. So in principle, we could also have just 2 different nodes. An example of a cycle is given by the node sequence 1, 3, 4, 1 and associated arc sequence 1, 3, 4, 3 and 1, 4. In this cycle, the arc 1, 3 is forward and the arcs 4, 3 and 1, 4 are backwards. Finally, a walk, path or cycle is said to be directed if it only contains forward arcs. The example of cycle that we just saw is not directed. An example of a directed cycle is given by node sequence 1, 3, 2, 1 and by arc sequence 1, 3, 3, 2 and 2, 1. Next, we're gonna study trees, which are a very special type of undirected graphs that we will be heavily using. A tree is an undirected graph that is connected and has no cycles. In the picture, we have an example of a tree. you can check that it is connected. In fact, for every pair of nodes, there exists a path joining them. For example, pick node 4 and node 8. Then a path from 4 to 8 is given by 4, 3, 5, 7, and 8. Of course, you should check that a path exists among every pair of nodes. It's also fairly clear from the picture that this example contains no cycles. A special type of nodes in trees is given by leaves. A leaf is defined as a node that has degree equal to 1. In our example, the leaves are the nodes 1, 2, 4, 6, and 8. Theorem 7.1 contains essentially all the results that we're going to use about trees. Point A says that every tree with more than one node has at least one leaf. We have just seen how in our example we actually have 5 leaves. Point B of the theorem says that an undirected graph is a tree if and only if it is connected and has a cardinality of n minus 1 edges. We can check this statement in our example. We know that we have a tree, so we already know it's connected. We have 8 nodes, so we should have 7 edges. 1, 2, 3, 4, 5, 6, 7. Point C of the theorem says that for any two distinct nodes I and j in a tree, there exists a unique path from I to j. Since a tree is connected, we already know that there exists at least a path from I to j. Point C then says that there cannot be two different paths from I to j. If we look at our example, we can easily convince ourselves that this is the case. We already saw earlier a path from node 4 to node 8, which was 4, 3, 5, 7, and 8, and you can easily check that this is the only path from 4 to 8. And similarly, you can check that C holds for every pair of nodes in our example. Finally, let's read point D in our theorem. If we start with the tree and add a new edge, then the resulting graph contains exactly one cycle. In our example, if we add the edge 1, 2, then clearly we have created the cycle 1, 3, 2, 1. You can check that this is the only cycle present in the new graph. So far, we've only read the statement of Theorem 7.1, and we somewhat checked that it makes sense by just checking that A through D hold in our example. Of course, this is not a proof. So now let's see how we can prove Theorem 7.1. I'm not going to write explicitly the proof for this theorem, but I'm going to explain to you the sketch of the proof with the help of some pictures. I leave it to you as an exercise to write a full proof of this theorem. Let's start with point A. We have a tree with more than one node, and we need to show that it has at least one leaf. We will prove point A by contradiction, so we assume by contradiction that there is no leaf. Since our tree has more than one node and it is connected, then every node has degree at least 1, but since there is no leaf, every node has degree at least 2. Let's pick a node in our tree. Let's say it's this node 1. The idea is to start building a path starting from node 1. Since the node 1 has degree at least 2, there is one edge that contains 1. Let's traverse this edge and reach a new node in our graph that we're gonna call 2. Now node 2 has degree at least 2. Therefore, there exists another edge containing node 2. Now from 2, we traverse this new edge and reach a new node which we're gonna call 3. Now we can repeat the same argument. The node 3 has degree at least 2, so it's contained in another edge. However, now if we traverse this edge, there are two options. Either we find a new node that we haven't considered yet in our graph, or we go back to some previously visited node. For example, it could be that we found the edge 3, 1. However, the second option cannot happen, because we're assuming that our graph is a tree, and in particular, it has no cycle. So this implies that at every iteration we need to find a new node in the graph. So if we keep repeating this operation, eventually we will have enumerated all the nodes in the graph, and so we have visited all our n nodes. However, we can now repeat once again the argument for our last node that we call n. N is not only contained in the edge connecting it to n-1 in our path, but there's another edge containing it. But at this point, we've already visited all the nodes in our graph, so this new edge must contain n and one of the nodes previously visited in our path. But at this point, we have created a cycle, and so we have obtained a contradiction. Therefore, we have shown that every tree with more than one node has at least one leaf. Now let's prove point B. This statement is an if and only if, so we prove the two implications separately. First, we prove the implication from left to right. So we assume that our graph is a tree, and we show that it's connected and has cardinality of n-1 edges. In the proof, we're going to use induction, and we're going to use part A that we just proved. Using part A, we know that our graph has at least one leaf. In the picture, it is this node I. So we can visualize the graph in this way. We have the node I contained in only one edge, and then we have the rest of the graph. Now let's throw away the node I and the edge containing it. So essentially, we focus on the rest of the graph. Now I claim that the rest of the graph is a tree. How can we show that? Well, we only need to show that this new graph is connected and has no cycles, using the definition of tree. Of course, it has no cycle, because if it had any, then also the original tree had the same cycle, which is of course not possible. So to prove that our new graph is a tree, we only need to show that it is connected. So let's pick any two nodes in our new graph. Of course, these two nodes were also nodes of our original tree. So there exists a path in the original tree from one node to the other one. Now everything we need to realize is that such a path could not have passed through I, because the only way that it could contain I is if such a path started from the first node, went to J, then to I, then back to J, and ended in the second node. But of course, this is not a path, because it passes through the node J more than once. So we have shown that our new graph, obtained by removing the node I, has no cycle and is connected. Therefore, we have shown that it is a tree. Now this new tree has one fewer node than the original tree. So by induction, it satisfies our statement. Hence, it is connected and it has cardinality of n-2 edges. Now let's get back to our original tree. Here it is. Clearly, it has cardinality of n-1 edges. This is because we're adding back exactly one edge. So now the only thing that we still have to show is that our original tree is connected. Since the rest of the graph is connected, we know that for every pair of nodes different from I, there is a path between these two nodes also in the original tree. So we need to show that there exists a path between node I and any node in the remaining part of the graph. This path exists and it can be constructed as follows. First, you construct a path from your node in the rest of the graph to J, and then you continue to node I. At this point, we have shown that our original tree is connected and has cardinality of n-1 edges. So this concludes our proof from left to right. Next, we're going to show the implication from right to left. So we assume that we have a connected graph with cardinality of n-1 edges, and we need to show that it is a tree. Let's say that this is our graph. If our graph has no cycle, then it's a tree and we're done. So let's assume that we have a cycle. Let's pick a cycle. Let's say the cycle over here. Now remove any one edge from this cycle, for example, the edge 6, 8. I leave it as an exercise for you to check that if you do so, your graph still remains connected. Now you keep repeating this argument as long as you have a cycle in your graph. For example, here we have the cycle 1, 3, 4, 1. And for example, we remove the edge 1, 4. Then we have the cycle 3, 5, 6, 4, 3. And we remove the edge 4, 6. Then we have the cycle 1, 3, 2, 1. And we remove the edge 1, 2. Finally, we have the cycle 3, 5, 7, 2, 3. In this case, we remove the edge 2, 7. At this point in our example, we have no more cycle. So we end up with a graph that is still connected and now has no cycle. so it is a tree. Now we use the implication left to right of the if and only if. So we know that our new graph has cardinality of n minus 1 edges. But remember that the graph that we started from had by assumption cardinality of n minus 1 edges. So we started from a graph with cardinality of n minus 1 edges, we removed a number of edges and ended up with a graph with still cardinality of n minus 1 edges. This means that in our process we never remove any edge. And this means that the graph that we ended up with coincides with the original graph. So also the original graph is a tree. And this concludes the proof of B. To prove C, we need to show that for any two distinct nodes I and j in a tree, there exists a unique path from I to j. Since our tree is connected, we know that there exists a path in the tree from I to j. So we only need to show that this path is unique, meaning that there exists no other path from I to j. So let's assume by contradiction that there exists another path from I to j, which is different from the previous one. But then it is intuitively clear that the union of the two paths contains a cycle. I leave it as an exercise for you to formally prove that these two paths can be used to construct a cycle. Such a cycle is therefore also contained in our tree. Of course, this is a contradiction because our tree doesn't contain any cycle. Finally, we prove D. We need to show that if we have a tree and add a new edge, the resulting graph contains exactly one cycle. Let's visualize it here in the example below. In this picture we have a tree, so let's add the new edge 2, 7. Since the original tree didn't contain any cycle, every cycle in the new graph must traverse the edge 2, 7. This means that such a cycle must be formed by the edge 2, 7 and then by a path from 7 to 2 that doesn't contain the edge 2, 7. So such a path is a path in our original tree connecting these two nodes. But in part C, we have just shown that there exists exactly one path connecting our two nodes in the tree. As a result, there can be only one cycle in our graph obtained by adding the new edge. And this is exactly given by the unique path between those two endnodes and the new edge. With this, we have completed our proof sketch of Theorem 7.1, and this concludes our video on graphs.